Hi everyone, I wanted to go through this assignment with you, and I get a lot of assignments where students are really struggling with calculating out these problems. So we're going to start by looking in the lesson and learning how to use these formulas correctly. I really encourage you to take notes on that and to have examples of those problems in your notes so that when you get to this lesson where you're calculating problems and turning it in for a grade, you have some examples to look at that you know are correct to guide you. You'll also see problems like this again on quizzes and tests, so you definitely need to have this information in your notes. So the object in this lesson's problems are going to have either gravitational potential energy, GPE. They will not have elastic potential energy, EPE, and that's a different formula. So the goal in the first type of problem is going to be to determine if an object has GPE, kinetic energy, or both. So GPE, if you remember, is gravitational potential energy. So we're looking at potential and kinetic, or the possibility of both. And then you're going to calculate the numerical value of each of those. And the goal in the second type of problem is going to be to determine the height or the speed of an object. And knowing its GPE or KE, you're going to have to plug in some different numbers. So that's what we're going to be working on. The formulas that we're going to be using, you can see are right here. So kinetic energy is calculated by half of the mass times the volume squared. And a lot of students are really struggling with this problem, and it does take a level of math skill to understand the order of operations and doing that correctly. And then this problem for potential energy is mass times the gravitational constant times the height. So a lot of students here are struggling with this number G, and it is the gravitational constant that is always, no matter what, 9.8, because we're dealing with the gravity on Earth. And that is a constant no matter where you are on Earth, and it's going to be 9.8 meters per second squared. So in any of the problems that you're calculating gravitational potential energy, you're using this formula and you're plugging in G, you are always going to use this number. So that's one thing that students are not reading and comprehending out of this lesson. All right, so we're going to go through and plug in these formulas together, and we're going to be using this Ferris wheel example. So it's going to be a couple little word problem. We're going to go through, just kind of dissect the formulas, and then we'll get into the actual lesson of 1.08, so we can look at that together. But I want to make sure you understand how to use these formulas first. So riding the Ferris wheel to the top. Once the Ferris wheel is loaded and gets to traveling at top speed, Jessie wants to know how much energy she has. When at the highest point on the circle, Jessie is 30 meters off the ground. The Ferris wheel spins at 5 meters per second at top speed. How much energy does Jessie, who has a mass of 50 kilograms, have at the highest point in the circle? All right, so how do you solve the problem? First, you're going to gather the information out of the problem. So we need to write down all the numbers that we have so that we can figure out what we're going to do with them. So we want to know how much energy. So we're solving for one type of energy that we don't yet know. The highest point on the circle, the height, that is 30 meters. The Ferris wheel spin is 5 meters per second. So it's going to be our velocity. And then how much energy does she have? She has a mass of 50 kilograms. So mass is going to be 50 kg. All right, so where is the object? So we're looking at the Ferris wheel spins, how much energy she have at the highest point. So to calculate here, where's the object? It is at the highest point, which is 30 meters. Okay, so that's our height. Is the object moving? If yes, what speed? We know it is. It's moving at 5 meters per second. And so what's the object's mass? We know that Jessie weighs 50 kilograms. So now we need to use these answers to complete the first part. Does the object have gravitational potential energy? Remember, an object has GPE if it has some height off the ground. So we do know that Jessie is 30 feet off the ground, or meters, I believe, 30 meters. And so now we need to plug in the numbers to solve for GPE. So if you take a look, you're just plugging in, you have 50 kilograms times 9.8 meters per second squared times 30, and that equals 14,700 joules. So that would be the potential energy in this problem. All right, so we know that it has potential energy because Jessie is the object, right? And she was not on the ground. The height was not 0, the height was 30. So now, does the object have kinetic energy? And we know that if it's moving, it does. And we know that, yes, it's moving 5 meters per second. So now, this one's a little harder, and I think this is where I said students are struggling, remember? So you need to set up the order of operations correctly. You're looking at half, and then if I were you, I would model this parentheses like they have here. Half of 50 times 5 squared. So remember, this is not 5 times 2, it's 5 times 5. You're squaring the number. So it's 5, it's the number times itself. So 5 squared, we know, is 25. So not 10. Students are putting 10 in here, and that is why that is incorrect. If you multiply the two numbers first in parentheses, 50 times 25, that equals 1250, right? So then we have to go back and look, we have that half thing to deal with. So we are taking half of that number. So half of 50 times 5 squared, which is 25. So remember that that was half of 1250. And that number is 625. So that is how they got 625 joules. Okay, so going on to another problem. Once the Ferris wheel is loaded and gets traveling at top speed, Jessie wants to know how much energy she has. When at the highest point on the circle, remember she's 30 meters off the ground, the Ferris wheel still spins at 5 meters per second. How much energy does Jessie have at the lowest point? So where is the object? So at the lowest point, let's say it's all the way on the ground, no height at all, it is 0 meters. So at that point, we know there is no potential energy. If we wanted to check that, all we need to do is plug 0 into the formula. So if we did that, we would plug in Jessie's mass of 50 times the gravitational constant of 9.8 times the height of 0. And you know when you multiply anything times 0, the answer is 0. So our GPE equals 0. That's why we know there is no potential energy here. The next part of it is the object moving, yes or no. It is moving, yes, just like last time. So you'll notice a pattern there. We have already calculated that out. So here it shows you 0, just like we talked about. And again, you have this same answer of 625 joules. That part did not change in this specific example. Okay, so we're moving to another example. Same Ferris wheel, same Jessie is 30 meters off the ground. It's still moving at 5 meters per second. When the ride slows down and people are let off, Jessie is stuck at the top. How much energy does she have now? Okay, so we're looking at this again. You can probably start to figure out she does have height this time. Our potential will go back to what it was before. She's 30 meters above the ground. So if we were to plug that in, she is the GPE we're able to calculate, and we know that she is not moving at the top while they're unloading. So let me see if it'll go to the next part here. All right, so looking at that, we would plug in the numbers here. Again, we've gotten this before, 700 joules. So we know that's the GPE. It's the same as it was before. And now we're looking at this problem. Does she have kinetic energy? Remember, it has kinetic energy if it's moving. So since she does not, she's not moving. No, because if you put that 0 in there for speed or velocity, it's 0. So there is no kinetic energy in this example. All right. So hopefully that part is helpful to you as we now take a look at this page. And I encourage you, we're going to plug in the numbers right at the beginning so we can answer 1, 2, and 3 without having to guess. But if we read through our situation, we've got a 2 kilogram bowling ball. So we know we need that information. It's 40 meters tall. So that's our height. Okay, 40. And then it's falling to the ground. If it's on the ground, that means the height goes to 0, right? So think about the potential and the kinetic energy here. So as it sits at the top of a building, okay, so that takes us down here to number 1. Does the bowling ball have more potential or kinetic energy as it sits on top of the building, and why? So we already know if the potential energy is calculated and we plug in, what do we have here? 2 times the 9.8 times 40, that gives us an answer. 2 times 9.8 times 40, 784 joules. Okay, so that would be our GPE at the top of the building. We know at that time the kinetic energy, it's not moving, right? The ball is not moving, it says it sits. So the kinetic energy, the KE, would be 0. So for number 1, your answer would be it has more potential because the ball is not moving, the object is not moving. So make sure you put the Y in there as well. As you go on to number 2, does the bowling ball have more potential energy or kinetic energy as it is halfway through its fall? Why? So a lot of students here are trying to guess, and what I encourage you to do is plug the numbers in and do the math. So if we calculate the GPE halfway through, you have a mass of 2 kilograms. You have the gravitational, the gravitational constant of 9.8 and the height of 20. Okay, so that gives us an answer of 2 times 9.8 times 20. That gives us 392. If we calculate the kinetic energy here, we've got to figure out 1/2 of the mass, so that is 2 kilograms, times the speed, which is 19.8. Okay, and if you remember, you have to square 19.8. So we're moving along here. We have 19.8 times 19.8. That is 392. Basically, there's a decimal in there, but it doesn't matter. Times 2, because we're multiplying it times the mass. So times 2 is 784. And you can kind of see a pattern developing here. And then we've got to take that half of that, because that's the part of the KE formula. So half of 784 is 392. So both of those are 392 at the halfway point. So these would be equal right here. Okay, these would be both 392. All right, so for number 3, does the bowling ball have more potential or kinetic energy before it hits the ground? Okay, so just before means it's not there yet. The height isn't 0 yet, but it's really close. We know that if you calculated all of that out, right, there would be more kinetic energy because the ball would be moving. Once it hits the ground, the ball would stop moving. So here you can say the kinetic energy would be higher because the ball is still moving. All right. And then as we go into 4, 5, 6, and 7, I think students, sometimes are just trying to answer these with words instead of calculations. It's looking for calculated work. You do need to show your work to get full credit. So let's go through these really quickly. What is the potential energy of the bowling ball as it sits on top of the building? We figured that out a little bit earlier, right? You're just calculating the gravitational potential energy. The ball is at the top, so you have the mass of 2 times 9.8 times 40. and that gave us an answer of 784 joules. So for number 5, what is the potential energy of a ball as it's halfway through its fall? We just calculated that. You would need to fill all of that in. So you're looking at the potential energy, 2 times 9.8 times 20. That was 392 joules. Number 6, now you're calculating the kinetic energy. I have a lot of students who are missing 6 and 7 because they don't know how to do that math correctly. So you're looking at the ball halfway through its fall. We just worked that out. Okay, you're using this formula of 1/2 parentheses, and then you have the mass, and then you have the velocity, and I can't really make that squared on here for you to see. You know, it would be kind of a mess to look at. So I'm going to put a little 2, but so you know that that's squared. So we know that we just calculated this out. The mass is 2. The speed was 19.8. So to solve it, first thing you need to do is square the number, 19.8 times 19.8. Then you need to multiply that times 2. That gave you 784. Then you divide that by half because you're dealing with this half up here at the front. So that answers 392 joules. Hang on, I got off on my notes. 1 second. All right, so as we're solving the last one on the kinetic energy, the ball before it hits the ground, you do have to look back up to get the speed. And it says, as it is just about to hit the ground, from falling off the building that is 40 meters tall, it is traveling 28 meters per second. So as we go back down here, we would need to calculate out 1/2 in parentheses 2 times 28 squared. 28 times 28 is 784. 784 times 2 is 1,568. And then you're taking half of that. We just did it. We multiplied it times 2. So you should start seeing a pattern there, but it's 784 joules. So that is how you solve these problems. Hopefully that was helpful. If you still have questions or there's something you don't understand, please email me or come and visit in Help Lab. Have a great day.